Today, on how it's made. Bowling balls. Barber poles. Felt. And radar guns. The bowling ball has undergone a lot of changes over several centuries to become such a striking success. From a crude stone to carved wood to rubber to molded polyester, it's been reinvented numerous times. But the latest version has turned out to be a real winner. Technological advances have reshaped the bowling ball at its very core. No longer round, the nucleus is asymmetrical, which causes the ball to curve towards the pins as it rolls down the lane. They make the cores from polyester resin, blending in minerals like barytes, silica powder, and limestone. The result looks like chocolate milk, or make that hot chocolate, because a catalyst triggers a chemical reaction that heats it up. As they pipe it into the molds, it quickly starts to cure and solidify. In just 2 minutes, it's ready to extract. This core is oblong, flat on one side with a knob. There are different versions of this core design, each one carefully calculated to manipulate the bowling ball's performance at a specific skill level. They now drill towards the center of the core to make a pinhole. This allows the core to be suspended in just the right position in a second mold. This asymmetrical core is about to be encased in a more uniform sphere. They tamp the core into the bottom part of the mold and then lock down the top half. After all, they don't want any leaks as they pump it full of plastic. It's a liquid polymer blend. A special chemical in it causes the mix to solidify slowly. It can take days for it to harden around the core, depending on the formulation and type of bowling ball being made. When they knock it out of the mold, all is revealed. That asymmetrical core is now sealed in a very symmetrical polymer shell. Next, it's into a third mold. This one will seal the bowling ball in an outer skin called the veneer. This veneer has been scientifically formulated to enhance the ball's traction as it hooks towards the bowling pins. It's made of colorant, plasticizer, a chemical called ISO, and urethane. Blending these ingredients produces high-performance polyurethane. As the mix flows into the molds, a chemical reaction causes it to heat up and solidify in just seconds. Then it's into an oven to boost the chemical reaction. Next, a spinning grinder shaves off the bump which was formed by overflow at the mold's intake tube. The removal of this bump rounds off the shape of the bowling ball. With its 3 layers, this bowling ball looks a bit like a big bonbon when it's sliced in 2. And while it may look sweet, it needs a bit more work before it's ready to take on the competition. A lift system delivers the bowling ball to a sanding operation, which roughs up the surface. The coarseness of the sanding varies, depending on the performance goals of the particular ball. This machine heat stamps trademark information onto the ball. They do one last sanding as a constant flow of water removes the powdery residue. The more polished the surface, the less pronounced the ball's hooking action will be. Even this last sanding is geared to a certain performance standard. Once they buff the surface, all that's left is to custom drill the finger holes. With this bowling ball in hand, success should be within striking distance. Barber poles go back to a time when barbers also performed surgery, tooth extractions, and bloodletting. Some believe that the idea for the red and white stripes came about because of bloody and clean bandages that twisted together in the wind as the customer held onto a pole during a procedure. Over time, barber poles have come to lose their gruesome connotation, but not their place as a historic symbol. There's only one company left in North America that makes them. They begin by rolling a printed liner onto a wooden mandrel. The mandrel they use depends on the size of the pole they're making. Using a knife, they score the liner at both ends. The liner is made of paper and vinyl treated with UV protection to prevent it from fading. Scoring the liner helps guide the worker as he trims the familiar red, white, and blue material to the required length. Next, he rivets the company logo to a support frame. Then, with bolts, he attaches a top and bottom support casting. The frame and castings are made of aluminum, so they're virtually rust-proof, which is a big plus since barber poles have to weather the elements. After ensuring that the assembly is level, they install the glass cylinder, which can be made out of extruded or hand-blown glass. After a final tightening, they double-check that everything fits snugly. Next, they add water to a special caulking powder and mix it to a smooth consistency. The caulking must be just the right thickness to properly fill the cavity between the aluminum casting and the glass cylinder. Five minutes later, when the caulking is dry, they carefully trim off the excess on both ends of the cylinder, leaving behind a smooth, watertight seal that helps secure the glass cylinder in place. Cleaning the glass by hand is just another example of all the artisanal handwork that goes into making these time-honored barber poles. Next, they mount the assembly on a hook and paint the caulking with a colored sealer that matches the casting and makes the caulking waterproof. After that, a worker puts in a motor mechanism. The motor will rotate the printed liner inside the glass cylinder. Once the motor is hooked up, he takes an inner cylinder, which has the printed liner mounted on it, and installs it on top of the mechanism that makes it rotate. He then installs a 2-socket light fixture with the bulb that illuminates the liner. To keep the printed liner straight as it turns, he then attaches what's called a top cylinder bushing. All that's left to complete the pole is to attach a rust-proof aluminum cover and the second light bulb that lights up the white glass globe. Finally, he hooks up the pole to electricity and makes sure the motor, both lights, and the inner liner are working properly, creating the illusion of movement. Modern barber poles come in various sizes and styles, with or without illuminating globes, but they always keep their link to the past. When production hits a snarl at the felt factory, things are going well. That's because felt is made by entangling fibers into a matted material. Felt has actually been around for thousands of years and may be the first fabric ever produced. These days, mechanization puts a new twist on felt. Boot liners are an example of the way felt layers our lives. They begin with bales of polyester fibers. Sometimes they add wool or another synthetic fiber. This machine is about to sink its teeth into those fibers. It's a rotating bed with hundreds of fierce-looking spikes protruding from it. An operator loads the bales of fibers onto a feeder conveyor. It shuffles the clumps towards that spiked conveyor, which snags the fibers and takes them up to another spiked rotating belt. But this one moves in a different direction to grab and pull the short, springy fibers apart. The process fluffs and blends the fibers, transforming the dense clumps into something that's the consistency of cotton wool. Now that the fibers have been loosened up, it will be easier to extract any metal bits that may have contaminated the bales early on. A magnet pulls out these contaminants, which would otherwise cause damage to equipment down the line. With the metal bits removed, the fibers move into another machine. This one has a series of pinned rollers that are close enough to almost touch. They rotate in different directions to align the fibers. This creates a uniform web of fluff. Then it's over to the cross slapper, a system of conveyors that move back and forth to neatly fold it up. Then they travel between rollers, which squeeze several layers down to a thickness of a little more than a centimeter. 10,000 long needles repeatedly stab the compressed web to entangle the fibers. Each needle is equipped with 9 barbs to snare the polyester fibers. This process is how they become enmeshed. It transforms the compacted fluff into felt. Rollers pull the matted material out of the machine. As they wind it onto a big roll, you can see that the fibers are now a solid mass. Next, they layer 2 plies of felt onto a metallized nylon film. This shiny film will reflect the outside cold. And the 3 layers combined will provide extra thermal protection that will even insulate against Arctic temperatures if need be. More long needles punch into the 3 layers and entangle the fibers to create one sheet of material. It's a form of laminating without glue. The needles leave little holes in the reflective film that improve the breathability of the fabric. Next, a worker uses a 25-ton press to punch boot liner patterns out of the felt. The press bears down on dies that cut out various sized insoles and boot liner side pieces. This felt is now ready to add a little warmth to someone's life. All they have to do is sew the parts together. The seamstress stitches the 2 side pieces using an industrial machine with needles that easily penetrate the thick, stiff felt. The top of the boot liner is finished, but without its sole, it's incomplete. They sew the felt sole onto it with a neat loop stitch, the only stitch that would hold this configuration together. From a pile of synthetic fibers to a rigid liner that's ready to protect you against the elements, it's been quite a journey. And it's far from over, as felt continues to keep its foothold in the world of layers and liners. If you see one of these, it's likely connected to the long arm of the law. Police have been using radar guns to nab speeders ever since the 1950s. They bounce radar off your vehicle and analyze the returning signal. And that's when sirens wail and the officer says, "Do you know how fast you were going?" If you're a speeder, the police have probably got your number, thanks to the radar gun. When operated properly, radar guns boast an accuracy rate of plus or minus 1 kilometer per hour. But of course, you can always try arguing with the officer. Making a radar gun starts with cable wire, lots of it. Rollers straighten it, then automated blades cut it to length and strip the plastic casing at both ends. With the wires now exposed, they're ready for the metal contacts that will allow wiring interconnections. A technician places the exposed wire in the contact and a machine crimps them together. They then assemble wires in various harnesses. These ones connect to a power cable and communications port. The technician inserts wires into a plastic connector to allow them to easily hook into a circuit board later. This little gadget is a microwave transmitter and receiver. It sends radio frequency energy to moving vehicles and then receives it when it bounces back. The red wires being soldered to its posts will deliver power to it. The white ones will return the radar signals. This special plastic lens will focus the radar beam. She attaches the transmitter-receiver unit to the funnel-shaped antenna at the back of the lens. Next, she solders wires to a circuit board. Some will carry power to it, others will deliver the returning radar signals for analysis. This second, smaller circuit board will process power from the police vehicle to operate the radar gun. An insulated metal plate shields the unit from interference from things like the police radio. The technician secures it with cable ties, and this radar module is now complete. She moves on to the display and control panel and snaps the keypad onto a little circuit board just below a light diffusing display window. She inserts the control panel hardware into a plastic faceplate and secures it with screws. As another safeguard against electrical interference, this plastic faceplate has been infused with metal. He wires the control panel to the power board to run a test. He checks all the digits and icons to confirm they display correctly. This machine presses melted plastic into the shape of a casing for the radar gun. A static discharger, worn on the wrist, dissipates any static electricity from the technician's body. This prevents damage to sensitive electrical components, so it's worn throughout the assembly process. She links the two computer boards, ensuring a good connection, because one will power the other. Then she installs the radar gun in the molded casing. She plugs the display assembly into connectors on one of the computer boards. Then she slides it into grooves in the casing. Now she hooks up this radar gun to a power source for a trial run. She taps the lens with a tuning fork. The gun responds to it as it would to a moving vehicle. If it functions properly, she installs the trigger switch. She closes the radar gun, securing the two-part casing with screws. A serial number and other identifying information goes on the side. In a final test, she connects the radar gun to a computer and aims the lens into a chamber. The chamber sends signals to simulate the effect of a moving vehicle, and the computer analyzes the gun's performance. You only have to look at a 35-year-old radar gun to see that this technology has come a long way. So it's ready if you try to pull a fast one.